Hello, and thank you all for joining us. Today's webinar, The Critical Nature of the Injection Unit to Molding Profitability, is being presented by the materials analyst, Michael Seppi. Michael has worked in the plastics industry since 1975 in a variety of roles involving both manufacturing and research and development. He is an independent consultant based in Arizona with clients throughout North America. Michael assists clients with material selection, designing for manufacturability, process optimization, troubleshooting, and failure analysis. My name is Trey McDonald with UL, and I'll be moderating today's event. Please send us your questions by typing them in the question box located on your screen. Our panelists will answer them at the end of the presentation. We are recording today's event and will send you a link by email when it's been posted to ulprospector.com. Now I'd like to turn the presentation over to Michael. Michael?
Thank you, Trey. Thanks, everybody, for joining today. I want to talk about an old subject. I know a lot of us are very mesmerized with new technology. We're always looking for the next big thing to come along, and it's always fun to get involved in the new stuff. But I think a lot of times we have these things that we've been working with for so long that we start to take them for granted, and we don't look to them as sources for innovation. And in my experience in molding and in consulting with molders, what I've encountered is the fact that the territory between the feed throat, when the pellets first drop into the screw, and the nozzle tip, where the material exits into the mold, is a key element in determining whether or not a process works or not. And there are some things that can be done to optimize this, just in terms of attention to detail and how things are set up. And there are some things that need to be done at an innovative level that are not being done enough in the industry, even though they've been around for some time in some cases. And these are things that can have a very, very big effect on whether or not your process actually runs the way it should. And so we're going to talk about those today. And the key elements I'm going to talk about yeah, let me just get myself going here. Okay. The key elements we're going to talk about today are going to be these that you see here. We're going to talk about the injection unit specifications. We're going to talk about screw and barrel and screw design. And then we're going to spend a little time talking about the non-return valve, that little devil on the end of the screw that can be the plus or minus and whether or not you actually get a repeatable process. And then we'll talk about the nozzle and nozzle tip selection. Now, the first thing I want to address here is injection unit specifications. Most of you know that for any given tonnage machine you look at, you have an option of putting anywhere from 3 to 4, maybe occasionally even 5 different size injection units on the machine. And that size is selected in such a way that it influences several different aspects of the machine's performance. The most important of these probably is the maximum amount of pressure that's available to you. Now, this is something that a lot of people who are not engineers and people familiar with machines may not know. So if you have someone involved in buying your machines who is strictly into procurement and has no technical background, they're not going to be aware of this. But the people out on the floor who have to work with the machine every day are. And once you buy that machine and put it on the floor, you're stuck with it for as long as it stays on the floor. And most people keep their machines, even though we talk about turning them over in 7 or 10 years, my experience is there's plenty of machines out there running that are 20 years old and up from that. So once you make a decision, whether it be a good decision or a bad decision about what you bought, you're kind of stuck with it. You're also going to be determining the length to diameter ratio of the screw, which is a key component of how well the screw functions in terms of homogenizing the material. And the diameter of the screw, which is the primary thing that varies when you change the shot size, as we call it, of the machine, also has a lot to do with how rapidly the screw turns in terms of an actual velocity around the circumference for a given RPM. So keep in mind that if you set 75 RPMs, which is a lot of times how we're kind of looking at screw settings, and you have a 1-inch diameter screw, that's a different rate of travel around the circle than it is if it's a 2-inch diameter or a 3-inch diameter screw. So these are things that are actual plastic conditions that we very often do not look at. We tend to look at machine conditions. And all these factors influence the condition of the polymer. And these factors will also affect how you develop your process conditions. So let's take a look at just one example of this. This is just a 600-ton molding machine. Doesn't matter whose it is. It's basically the same deal throughout. We tend to talk about our machines in terms of two conditions, the tonnage and the shot size. Shot size being the maximum amount of material we can actually deliver if we stroke the entire travel of the screw from all the way back to all the way forward. And we basically couch this in terms of the weight of material that we can extrude in terms of general purpose polystyrene. So in this particular case, we have the option of a 41-ounce barrel, a 54-ounce barrel, or a 68-ounce barrel that we can buy with this 600-ton molding machine. Now you'll notice that the row that says screw diameter, this is the primary way that the machine manufacturer changes that volume, changes the amount of material that can be delivered. And the difficulty with this is that when you change the diameter of the screw, when you make it larger, the machine itself, if it's a hydraulic machine, the ram that is receiving the pressure from that oil is not changing in size. And we have this thing called an intensifier. It's the amount of pressure of the oil pushing against the ram, which translates the amount of pressure pushing against the plastic. And the intensifier essentially is the ratio of the areas of the ram to the screw. If the diameter of the ram stays the same and the diameter of the screw increases, then the intensifier goes down. And you can see the effect of that in the bottom row of this table. You can see that the maximum available pressure that you have on the 41-ounce screw is almost 27,500 psi, whereas the largest barrel only gives you a pressure of about 16,600 psi. Now, why is this important to us? Another way of looking at this, by the way, if you look at some of your machines, many of your machines will have this little plate that looks a lot like this, usually at the injection end of the machine. It might be affixed right to the barrel. It might be a little bit below the barrel. But this is another way of illustrating and understanding that these three barrels that you can buy with this particular machine bring with them a different relationship between the hydraulic pressure and the melt pressure that is actually generated on the plastic. So here you have a 25-millimeter barrel, which is the smallest barrel you could buy, and a 2,000 psi hydraulic pressure translates to a 25,000 psi melt pressure. So that's about a 12.5. It is a 12.5 to 1 intensifier. The next size barrel up, that same 2,000 psi hydraulic pressure only gives you 20,000 psi of melt pressure, and the largest of the barrels only gives you 15,000. That's a pretty big spread, just based on the size of the barrel that you decided to purchase with the machine. Now, this is a schematic that John Bazzelli provided that I'm using, and you'll see his name quite a bit in this presentation today because John's done a lot of the work on this and has been working on this for quite some time, and then encounters this on a regular basis when he goes into plants and finds out that people are running a machine with insufficient pressure to actually make the part that they're trying to make. And the genesis of that is that they do not have a large enough intensifier. The ratio between the area of the ram and the area of the screw is too small. Consequently, the hydraulic pressure doesn't turn into enough plastic pressure. Now, in this case, this is a pretty good machine, 16 to 1 intensifier, so a 2,000 psi hydraulic pressure generates 32,000 psi of plastic pressure. And for most applications, this would be what would be considered an internationally competitive machine. Now, the reason this number is important to us, this melt pressure number is important to us, is that any time we move polymer, we experience a delta P, something called a pressure drop. And that pressure drop is captured for a round cross-section anyway by this equation. Not a very complicated equation. There's a couple of factors in here we need to pay attention to. This factor here, this mu, that is the material's viscosity. That is what we're always concerned about, and this is what we're always trying to manipulate with our process conditions. And we'll talk in a little bit about how we adjust viscosity. Q is the volumetric flow rate. Think of this, if you're a processor, as your injection speed. Not the injection speed you have set on the machine, but the actual speed with which the screw moves forward as it travels through the process of filling the mold cavity. L is the length of the flow path. This is pretty much governed by the size and shape of the part and where you chose to put the gate or gates. The longest distance you have to cover from the time the material enters the mold to the time it reaches the end of the cavity. That is your limiting factor for your flow length. And then in the denominator, we have this factor, and this is basically the diameter of your flow path. If it's round or if it's rectangular, this would be AB cubed, where A would be the width and B would be the thickness. But essentially, it's the geometry of the path through which the material is flowing. So obviously, as your flow paths get thinner, as your walls get thinner, and as your flow paths get longer, as your part becomes more complex, or as you go from an 8-cavity mold to a 16-cavity mold or a 32-cavity mold, these two factors are going to drive an increase in delta P. Now, if you're going to make a full part, obviously you have to have pressure everywhere in the cavity. And the general rule that we observe when we put cavity pressure transducers in a mold is that in order to have what we call a packed out part, a part that looks good and is dimensionally stable, reflects the surface finish of the tool, you typically will want to have about 2,000 to 3,000 pounds of plastic pressure at that point in the cavity. So if you have a machine that can generate 27 or 28,000 psi, you can afford to lose a lot more pressure and still get there than if you have a machine that can only generate 16 or 17,000 psi. And many times when a molder comes to an end user and says, we can't make this part in this material, what they really are saying is, we don't have a machine capable of generating enough pressure so as to drive this material the distance that you want it to go. And the reason a lot of times for that is because of the way the machine barrel was sized when they bought the press in the first place. Now we can document pressure losses all the way through a process, all the way through from the nozzle all the way through to the end of the flow path of the part. There's a technique which we can't go into today called a pressure drop study. This is the result of that pressure drop study. It shows where pressure is being lost. So you lose a little bit of pressure going through the nozzle, you lose a little more pressure going through your sprue and runner, you lose a very small amount going through your gate, and then you lose a fair amount just in the act of filling the cavity, driving the material from the beginning of the cavity to the end of the cavity. So then the question is, how much pressure would you have to have in order to effectively and repeatably make this part? Well, if you add the numbers together, you get this value, 22,548, and people would say, well, if my machine can generate 23,000 psi, then I'll be fine. But there's some things that go in on top of this 22,500 psi, not the least of which is the natural resistance of the system. Whether you have a hydraulic machine or an electric machine, there's a certain amount of inertia required just to push the hardware, the screw. And to move the screw, even if there's no plastic in the barrel, if you move a screw that's empty through an empty barrel, you will still get a pressure reading. And that pressure reading is just the natural resistance of the system, the natural inertia of the system. And for different machines, that number is going to be a bit different, but it can be anywhere from 2,000 to 3,000 psi, which must be added to this 22.5. Then you have to account for the fact that you're going to have lots of variability in your resins. You're going to have a variation from one batch of material to another batch of material, even if it's made within specification. Just like we have tolerances in the molding business, the resin suppliers have tolerances in their business as well. And if you're buying a 10 melt flow rate material, you might get a batch that comes in at 9 on one week, and you might get a batch that comes in at 11 the next week. Well, if you develop your process with an 11, and all of a sudden one day you receive a 9, your machine's going to have to work a little bit harder to push that 9 melt flow rate material. Not a lot harder, nowhere near as much as you might think, but still there'll be a measurable difference. So there has to be some allowances for normal variation in your input of your material. And then if you're running a hygroscopic material, let's say a nylon or a polycarbonate, what you'll also realize is that the moisture content of the resin on any given day is going to influence its viscosity. If you dry a nylon to a very low moisture content, its viscosity will be higher than if you dry it to a mid-range moisture content. So it's another variable that you put into the system. And by the time you get done stacking all these variables up, in order to really be safe, that you can produce the same part the same way all the time, which is really the name of the game, you should be running in the neighborhood of 30,000 psi. That should be the capability of your machine. Now you'll notice none of the numbers I showed you in the previous slide came up to that level of 30,000 psi. So the question then becomes, how many molding machines out there running today can deliver 30,000 psi? And there are plenty of applications out there that require more than this. And as we get into thinner walls, we get into longer flow paths, you're going to see more and more and more parts that require machines to be able to produce pressures of 32, 35, 40,000. I've worked on a machine recently that could generate 49,000 psi, and it can do things that many of your machines cannot do. Many things that it can do you would consider to be impossible. So what happens when you don't have the needed pressure? Because the needed pressure, an abundance of first stage pressure, for those of you who are involved in scientific molding, you know that first stage pressure, an abundance of first stage pressure is required in order to have velocity control. And the reason velocity control is important, as we'll see in a bit, is because velocity governs the shear rate that we're applying to the material, and shear rate is a key component in controlling viscosity. Well, without enough pressure, you're stuck with running a pressure-limited process, which means you don't have velocity control, which means you have poor process control. Your process will become overly sensitive to normal process fluctuations. I always know when someone's having difficulty running with enough pressure because they'll call me up and say, well, you know, the batch we ran before had a flow rate of 8 grams per 10 minutes, and it processed fine, and now we're running a 7 and we're having difficulty. If that's happening to you, you either have the machine set up to be artificially capped at too low of a pressure, or you have a machine that is pressure limited. The other thing you'll typically do, and we see this all the time, is you'll go to your customer and lobby for a higher flow material. What we need to understand is that when you ask for a higher flow material, what you're usually asking for, 99 out of 100 times, you're asking for a material with a lower molecular weight. And molecular weight is what drives performance in plastics. So a lower molecular weight means lower performance. So when you go to your customer and say, I can't process this 2 melt flow polypropylene, I need a 10, what you're really saying to them is, I need you to accept a material with inherently lower capabilities to perform than the stuff you're asking me to process. If they're knowledgeable, they're going to push back because they know that's what you're asking for. If they're not knowledgeable, they may say yes and then find out too late that they've agreed to something that causes them problems when the part gets out in the field. The other option you have is to lower the viscosity of the existing material. And we have 2 tools for modifying viscosity in a polymer. One is the temperature of the material, and the other is the shear rate. Well, we've already talked about the fact that shear rate's related to velocity, and if you don't have enough pressure, you can't change velocity. So now you're stuck with one option, and that is to increase the melt temperature until the material starts to flow the way you expect it to flow. This is a graph that shows you the dual effects of shear rate and temperature on the viscosity of a material. This happens to be a polypropylene, so you see 3 different temperature curves here, one generated at 400 degrees Fahrenheit, one generated at 440, and one generated at 480. And you can see that at any given shear rate, the viscosity does come down, not very much, but a little bit, as a function of increasing temperature. It also comes down quite dramatically as a function of increasing shear rate. So these are the 2 tools that we can employ in order to arrive at what we consider to be the ideal viscosity for the material, assuming you have a machine that can manipulate both of these variables at the same time. Now, what I almost always encounter when I walk into a molding plant is material running at a temperature higher than it should have to. And very often the reason it is because people are out of speed, they can't increase the shear rate anymore, so all they can do is increase temperature. And by the way, this is the equation that governs shear rate. Again, a simplified equation for a round cross-section, and a simpler equation than the one I just showed you. Notice that Q is in this equation. This is your injection speed, and R is in this equation. That is the velocity of your, or the geometry of your flow path. This is one of the reasons we get away with restrictive flow paths, because as we go to more and more restrictive flow paths, our shear rate goes up. When our shear rate goes up, as we just saw, our viscosity goes down. And so there's a point at which we reach a point of diminishing returns, and the flow path becomes too small, and the pressure drop goes up faster than the shear rate goes up, and that's where you start to reach your balance point. If you're doing flow simulation, these 2 equations I just showed you, these are the 2 equations you're supposed to be balancing, because every process has an ideal balance between shear and temperature. And if you do your process development right, you find that balance point and you stick with it for the rest of the life of the product. If you don't, then you're kind of guessing a lot of the time. Now, I mentioned before that most people I run into are using melt temperatures that could afford to come down. And a lot of times there's a lot of denial associated with that. A lot of times you come in and say, well, you can turn that temperature down 20 degrees. No, we can't. No, we can't. And then when you get into it, you find out, well, yeah, you really can if you're willing to use the capabilities of the equipment to their fullest and if you have the right kind of equipment. But let's assume that you are running higher melt temperatures than you need to. There's a cost to this, and there's a cost to this that is very often not recognized. Remember, we're talking here about profitability. The more heat you put into a material, the more work you have to do to get it out. And that translates to longer cooling times, and cooling time is the largest part of your cycle time for the most part. So longer cooling time translates to a longer cycle time. Longer cycle time means you're not making as many parts per hour, and that's your bread and butter. Your material cost is basically a pass-through. You're selling machine time. So if you're not making good use of the machine time, it's costing you money. Also, higher melt temperatures mean higher energy use. Higher melt temperatures mean an increased chance of polymer degradation, which damages the properties of the material. It also means the increased consumption of important additives that are needed for use while the product's in the field. And if you're using your regrind, it also means that your regrind is of a lower quality because it's been subjected to more punishing conditions than it should be. So there's a lot of things that add up here to take away from the integrity of the material as well as the efficiency of your process. Now, this is some work that was done a number of years ago. You can find this published in one of the medical device documents. It's a very telling piece of research because it illustrates how important the right melt and mold temperature are to the properties of a material. This happens to be ABS, and we all know ABS to be a fairly tough material. One of the corollaries of running a melt temperature too high is that usually what goes along with that is people are running their mold temperature too low, and they're doing that to try and get the heat out faster. And what you'll notice here in this graph is that mold temperature in particular has a very dramatic effect on the impact strength of the material. The warmer the mold, the tougher the part, because a warm mold produces a part with less internal stress. Cold molds may look like a good idea for cycle time, but they produce a material that does not have everything it's supposed to have. So a warm mold and a cool melt produce a very, very tough part. A cold mold and a hot melt produce a material with very, very little of the impact that the material is intended to have. So there's a great deal at stake here in being able to set your machine up the right way so that the material gets treated the way it wants to be treated. And all this starts, remember, with having a machine that can develop enough pressure so that you can drive the material at the right speed so that you do not have to over-rely on temperature to get the viscosity you need. As I mentioned, developing a process is really the business of balancing shear and temperature. Shear is controlled by the rate at which the material flows and the geometry of the flow path. Higher shear rates give you lower viscosity, which is another good way of keeping the viscosity down to where you can manage it. And there's always an optimal balance of shear and temperature for every application. In my experience, commercial processes tend to overemphasize the role of temperature and underutilize shear in controlling viscosity. Now, temperature is not trivial. If you look at a material like polycarbonate, you can see that the effective temperature is a lot more dramatic than it is in a material like polypropylene. So you have to kind of work with what resin you're playing with. It's also important to understand that the hotter the material gets, the less efficient shear is in reducing viscosity. And you can see that in this graph. The polycarbonate running at the lowest temperature experiences a larger decline in viscosity with increasing shear rate as a percentage of where you started than does the material running at the higher temperature. So as you raise the melt temperature, you're lowering the effectiveness of the adjustment related to shear rate. So there's an interplay here between these two variables, and it needs to be well understood. Here again, this is what your flow simulation software, if you're running such a tool, is supposed to do for you. But you have to be able to interpret the data in such a way as to get this information out of it. Now, the other problem we have in this industry is that shear is very often considered to be damaging to materials. It is true that there is some heat generated when we shear a material. We know that to be the case. We don't know how much, and the answer is going to be different for each material. We are still working out the details of how much temperature truly is contributed by higher shear rates. What I have seen, though, is that whatever the contribution is, it tends to be overstated. People tend to think they're doing a lot more damage than they really are. Shear up to a point is not a detrimental thing, it's a beneficial thing. You just have to keep from going too far, just as the same way with temperature. Even if shear heating does occur, what we do know is that it only occurs during the time when the polymer is flowing rapidly into the mold. For most processes, this is over in a matter of a few seconds, maybe less than 1 second. If, on the other hand, you choose to add the heat by turning up the temperature of the barrel, that heat is applied for as long as it takes for the material to make its way through the entire injection cylinder. And that, at minimum, is going to be 3, 4, 5 minutes. In many cases, it's a lot more. I've seen residence times in excess of a half an hour. So you ask yourself, would you rather expose the material to high heat for a few seconds or for 30 minutes? And I think that the answer is pretty obvious. This is a study we did a number of years ago with a company that was being badgered by their customer to slow down the injection speed because they were, quote unquote, harming the material, and the material they were molding was PEEK. If you're degrading a material to too much shear, there's a real easy way to tell. Just simply run a melt flow rate test on your raw material and then run on the molded parts. And if the molded part melt flow rate is much higher than that of the pellets, then yes, you're doing some damage. So we have a lot of data here. We have two parts, first of all. One we call part 1, which was run through 3 different processes. Notice this injection speed was the one the molder wanted to use because this is what gave them full parts repeatably. And this is the one that the end user wanted them to use. They had an advanced degree guy hovering over them while they were developing the process, telling them that any shear rate that exceeded a certain value was automatically going to damage the material. And you can see that there's virtually no difference in melt flow rate between the slowest speed and the fastest speed. Same thing happened with part number 2. Now you notice that these 3 processes, D, E, and F, develop a much higher melt flow rate than A, B, and C. What did we do here? We raised the temperature of the barrel in order to be able to slow down the speed. And this is where we actually did the damage to the material. Not that this is damage. This is still acceptable, but it's marginal. So it's a good illustration of the dual role of temperature and shear on how a material is truly influenced. You have to really put numbers to this and not just kind of engage in a lot of mythology. And there's a lot of mythology out there in our industry. We all know that. 2 other things I want to mention about injection unit specifications before we move on to the Sprue. And that is, first of all, you need to make sure that your system is load compensated. What I mean by that is, if you're running under velocity control and it's taking you 2 seconds to fill the mold, to fill it the way we consider filling in scientific molding, which is 95, 96, 98% full. If it's taking 2 seconds to deliver that material to the mold, then when you pull the injection unit back and on cycle, you shoot that same volume of material into the air with no resistance, it should take the same 2 seconds. Now, ask people in the industry about this. Pose this question to them. How long should it take for that same amount of material to travel into the air as it does into the mold? Most people will tell you the injection unit should go faster. It shouldn't go faster. If it does go faster, then it's what we call load sensitive. And that's a problem, because what it means is as your viscosity changes, your injection unit will not be able to maintain the same speed, which is the name of the game. Now, if you're load sensitive, you don't need to go out and buy another machine. There are kits you can buy that you can put on the injection unit hydraulic side that will actually fix this problem. And they've been around for a long time. But it's something you need to look at. Most machines built today do not have this problem. I say that with some caution because we all know we live in a global economy, and there are a lot of people building machines now in far-flung places of the world that are going through the same learning curve we went through in the 70s and 80s. So don't take anything for granted. The other thing is velocity linearity. When you look at a machine setting and you plug in and you say, go 40 millimeters a second, don't take it for granted that the machine is actually doing what you told it to do, because when you get up into the higher realms of what the machine's capability are, you're going to find out that it can't necessarily do what you're telling it to do. And so there's a study you're supposed to do where you basically set the injection velocity at different points and then actually record the velocity you actually get. And what you'll get is a curve that looks like this. And you'll notice that the actual performance of this machine tracks pretty well against the theoretical line until you get up near the top, and then you start to level off. And this happens with every machine that I've ever worked on. In some cases, it starts a lot earlier, which is not good. You'd like it to start late in the game, but at the very least, it's going to happen when you get out here. So these are things that you really want to know about your machine rather than assume. Now, let's talk about the screw for a moment. This is a picture of our general purpose screw. This is what's running in 99+% of the machines that are out there in the world today. This is what gets installed when you buy the machine. This is what your machine supplier is giving you, unless you make special requests, and even then you may find that they're not equipped to honor those requests. I have a colleague by the name of Bob Dre who has worked in the extrusion industry for a long, long time, probably 45, 50 years, and Bob calls this a no-purpose screw. His contention is that the screw that we in injection molding typically use does not do what it's intended to do, which is to produce a homogeneous melt, a melt that is of the same temperature and the same consistency throughout. And if you don't believe that this is the case, all you have to do is try to mold a material like, say, polycarbonate in a color where the color is being applied by adding a color concentrate, and see how difficult it is to produce a part that is free of swirls and free of color variation. That's a visual indication of a lack of homogeneity. But understand that even in a pre-colored material, that same lack of homogeneity still exists. And what it means is we're delivering material to the mold that is of different temperatures in different areas. That means it's going to cool at different rates. That means it's going to shrink at different rates. And that means that it's going to impact our ability to control dimensions, control warpage, so on and so on and so forth. Now, the geometry of these screws is pretty predictable. You have a particular amount of flights that are devoted to what's called the feed section. You have a particular amount of flights devoted to what's called the transition section. This is where the melting process actually is supposed to start. And then you have the metering section. You'll notice that the depth of the flight gets shallower, gets smaller as we move from back to front. The ratio of these flight depths is what we call the compression ratio. And very often what people will counsel you to do is use a compression ratio that is optimal for the material you're processing. Sounds good. Only problem is if you're a custom molder and you're running polycarbonate one day and acetal the next day, you would need two different screws. And we don't like to be changing screws that often. So that's not necessarily the best idea. The model for this, and the reason we have a problem with this design, is because as we develop the melt pool, and the melt pool and the solid bed are traveling forward, if, and this is usually the case, not if, but when we get to the front, and we don't have all the pellets melted, the solid bed eventually will break up, and it will basically now become like ice cubes in a glass of water. Getting these melted when we no longer have direct access to them, the direct ability to generate the compression and the mechanical work that's designed to produce the heat needed to melt the material, produces a whole range of symptoms, like the color swirls I mentioned, like unmelted pellets, which many of us have seen, especially when we're running semi-crystalline materials like nylons and acetals and polyethylenes. Excessive screw wear because we have pellets getting in between the barrel and the flights, and when they're really hard and rolling over the flights. And so what we typically will do is we'll raise the temperature of the material to try and get these last few pellets melted, which is kind of like taking a glass full of ice water and taking a propane torch to the glass in order to get the ice cubes melted. You will get them melted, but in the process you'll overheat the rest of the water. And that's not necessarily what we're trying to do. We're trying to get the whole glass of water to be the same temperature. And so this involves gentle distributive mixing. And by the way, this problem becomes magnified in lower L over D screws. So if you're running a 20-to-1 screw, you're going to have better success in melting and homogenizing than if you're running a 16-to-1 screw. And if you go back to that table we showed you at the very beginning, remember that one of the other things that happens as your screw diameter gets bigger, because the screw length doesn't change, is that your L over D is going down as your screw diameter gets larger. So that's another thing that's happening when you buy the bigger barrel that is going to handcuff you in terms of getting a good process. So there's a lot of work that's been done in the last 20 years. Not enough, unfortunately, but there's been some work done. And we don't have time to go into all the possible designs that you can access out there. But suffice it to say that there is this alternative of what we call a barrier design. And there's a lot of devil in the details of how this barrier is machined. But this will improve the performance of the screw to a significant degree. And we call these mixing screws, we call them barrier screws. There's a lot of different ways of doing this. There's been some good work done going back as far as the early 90s on how to design screws. And I can tell you, I went to a paper that was presented back in 1990 in an Antec where John Bazzelli and a guy named Bruce Larkin talked about work that they had done in improving the performance of a machine that was running ABS that was being colored with color concentrate, and the molder was having all kinds of defects and problems with color swirls and uneven color and things of that sort, and just made huge, huge changes, hundreds of thousands of dollars of savings across the product line by implementing this new screw. And it really stuck with me. And it went back to my plant, and we were struggling mightily with a job of our own, and this is the human nature side of things, is, you know, you don't sometimes make changes until you're in a lot of pain. And we were in a lot of pain. We were hemorrhaging dollars down on this one machine running a very different material from the ABS that they talked about in their paper. We were running acetal and having unmelted pellets and having char forming in our screws because we were running the material too hot, producing excessive amounts of formaldehyde gas. Most of you who've run acetal know that that's one of the byproducts of running this material. And we switched out the screw and saw such dramatic improvements in our throughput, in our reject rates dropping, that we calculated that the screw paid for itself in 6 months. And it made such a deep impression on our operations people that over the course of the next 5 years, we replaced virtually every screw in the plant with a mixing screw. We no longer had general purpose screws in our plant anywhere. And the number of quote-unquote processing problems and the number of quote-unquote material variability issues that just simply disappeared was absolutely remarkable. And this is one of the reasons I'm talking about this today, is because most people never have a chance to experience the difference between doing it the way we've always been doing it and doing it with this modification in the hardware that allows us to get out of the very same materials much, much different results. Now, when you get into mixing devices, be a little bit careful, because most of the mixing devices that have been developed, especially in the early years, to improve homogeneity in materials are very high intensity, high shear devices. Things like Matic mixers and Dome Edge mixers and Saxton mixers. You look at the design of these things and you see, well, we're really beating the heck out of the material. If the material is very shear tolerant, a material like polyethylene, for example, you can get away with this. But you're not going to be able to do it with materials like ABS, polycarbonate, polysulfone. You're going to need gentle distributive mixing. And that slide I showed you previously is what is designed to achieve mixing without getting too heavy-handed. And so this requires a lot of attention to detail. Not all mixing screws are equally effective. You've got to do your homework, and you may have to do some trials. I've gone into places where people say, well, we already have a mixing screw in there. And you say, yeah, but you're not getting the mixing you need. And we pull that screw out, and we put a different design in, and we get different results. Now, screw and barrel wear. This is a nice cross-sectional view of how the screw and the barrel fit together. Notice it's very long, and it's very small in diameter. So obviously things like straightness and concentricity are very, very important. Because these materials are going to be very, very close to one another, ideally just 2 or 3 thousandths difference between the outer diameter of the screw and the inner diameter of the barrel. You want compatible materials in case they do rub against one another. And your process has to be set up properly. You have to have the right screw rotation speed. You have to have the right barrel temperatures, the right back pressure. These are all things that have to be developed during your process development cycle. And of course, your polymer and your fillers. But understand that it doesn't require a high degree of glass fiber in order to wear out a screw. I've seen amazing amounts of screw wear in machines running nothing but high-density polyethylene, simply because the material is not melting at the point where it should be melting, and so you're getting an awful lot of pressure being developed between the screw and the barrel wall with material that's still in the solid state when it should no longer be in the solid state. Any of you who've been out there long enough to really experience a wide range of molding processes has seen this happen, so you know this occurs. Now, symptoms of wear. You may see screw rotation during injection. This is probably the check ring, the so-called non-return valve, which we'll talk about in a minute. The inability to hold a cushion, also usually the problem of the non-return valve. You may see extended screw recovery times. You may see dark streaks and burned material. You may see extended color changeover times, even if you're using a good purging compound. You may start to notice tramp metal in your parts or in your melt delivery system. These are all signs that things are starting to wear out. And wear is a gradual process, so it can be kind of insidious. It kind of robs you before you even know you're being robbed. And of course, the result is lost profits. Now, ironically, one of the things that happens when you start getting wear is you may actually see better distributed mixing, because with wear comes this random process of the material not feeding forward as efficiently as it might. And so very often, you'll hear people complain, well, you know, I just put a new screw in and I'm getting worse mixing than I did before. Well, that's because now the material is moving forward the way it's supposed to, and the true limitations of your system are now exposed. Now let's talk about the non-return valve for a minute. This is designed to prevent backflow of material during injection. Obviously, if you're going to put the same amount of material into the mold cavity every single time, you've got to be able to control where the material goes. And so the non-return valve is designed to keep pressure on the material and prevent it from going backwards. This component will tend to wear faster than the screw and barrel, so it tends to need to be replaced more often. The geometry of the valve is a balancing act. Once again, a balancing act of shear with sealing. Anything that seals really well will have very restricted flow paths, so the shear rates will be relatively high. Anything that doesn't generate a lot of shear will have to have more liberal flow paths, and it may not seal as well. And so here again, you may find different requirements for high flow materials like nylons and polyethylenes, and low flow materials like, say, polycarbonate. And this is just one of the things that we battle when we deal with these little devices we call non-return valves. When you look at the way these things operate and you understand the dynamics of plastic, you realize the mechanics of valve operation result in inherent variability. And this is a problem because, you know, we talk a lot very casually about Six Sigma and zero defects and things of that sort, and you know, being able to make 1 million parts without any defects. But if you have a piece of hardware in your machine that can't do the same thing 5,000 times, then the likelihood you're ever going to get there, and the reason you're not getting there, is very much a nuts and bolts issue. It's not about necessarily, you know, the processing acumen of the people on the floor. It's about the hardware in many cases. There have been a lot of different enhancements to improve consistency that have been attempted. There's a device out there called the QSO, which is spring-loaded to try and make sure that the ring goes back right away to where it belongs, you know, things of that sort. But if you talk to people who've been around long enough, you know, they kind of use the terminology that there are two types of non-return valves, those that leak and those that will. And unfortunately, this is true. Now, this is the old ball check non-return valve. This device is very, very effective at shutting off. Unfortunately, the flow path is very restrictive and generates a lot of shear. So it works really well for commodity materials like polyethylene and polypropylene and maybe polystyrene, but it's a lousy alternative for materials like, say, polycarbonate or polysulfone or even ABS. So most of us are using what's called a sliding ring screw tip, 3-part, 4-part, however you want to do it. And when the screw is traveling forward, we are basically sealing off the surface of the check ring against what's called the backup washer so that the material can't go backwards. So when we're generating pressure, the material has to go forward. When we're rotating the screw, the ring floats forward and allows material to float underneath this area and then on through. And what I was talking about before, the restrictiveness of this flow path is a big part of whether or not the material experiences too much mechanical work going through this area or whether or not it survives this little trip through here. But the challenge is that when the ring is here and the screw starts forward, how rapidly does that screw get back in position so as to truly fulfill its function? Now, there's a lot of clues out there about what we should be doing from other industries, and this is a good example of one of those. When we design a screw tip, we typically are trying to shut off against a large area. We're trying to match these areas faithfully. If you look at the way an engine valve works on a car, they don't try to do that. The actual point of contact where the valve is shutting off is actually a very small percentage of this area here. And that results in a much more repeatable function of the machine. So here again, looking at an old piece of hardware in a new way, this is a new approach to the design of the screw tip with a check ring and a backup washer that have a much smaller contact area, and this produces a much more repeatable function. Now, you're not going to get these off the shelf. The difficulty with a lot of these new developments is it's very hard to find someone to build these things for you, but people are trying these, and everyone I know who's tried them has said, yes, this makes a huge difference in the repeatability of my process, because now I'm only trying to shut off on a very small area, and I can do this much more repeatedly than I can trying to shut off against this entire area here. Okay, and finally, I talk about picky details, the nozzle and the nozzle tip. A couple of things to consider. First of all, where the thermocouple is, because what temperature do we want to know when we talk about a nozzle tip? We want to know about the temperature right here. And so the further away the thermocouple is from the point of interest, the more likely it is that we're getting a reading that's poor. And also it's causing the heater to turn on and turn off at the wrong time. The other thing we need is a nice streamlined flow path. So we're preventing pressure drops. And as we know, not sure why this ever happened, but history is history, we have two different radiuses out there for our mold, so we need two different radiuses for our nozzle tips. So you need to make sure if your mold has a 3/4 inch radius, so does your tip, and your 1/2 inch radius has the same radius as the mold. And the fundamental thing that makes this a challenge is the fact that this nozzle tip is up against a piece of metal with pressure applied that is probably 300 to 400 degrees Fahrenheit cooler than the material that's flowing through it. And so it's naturally an area susceptible for freezing off. This is an area we really have not done a lot of work on. Most of the time, we all know what we do if we're processors. We put a piece of cardboard in there, and we hope to heck that reduces the amount of heat transfer between the nozzle tip and the sprue bushing. One thing you do not want to do is you do not want to use this kind of nozzle tip. This is what's called a general purpose tip. This has a straight flow path. This area here constitutes a dead spot, and this represents a very long land, which is a big pressure drop. It's hard enough to get the plastic to go in where we want it to go without making life more difficult by putting nozzle tips on the end of the machine that make it even worse. So if you have these in your plant, do one of two things. Drill them out so that they look like what I showed you before, or throw them away and don't buy any more. Simple as that. Two kinds of tips you should be able to use. Reverse taper geometry for those materials that have sharp melting points where you need to keep the heat further back in, and free flow tips for everything else. Most of us talk about nylon tips and ABS tips or nylon tips and everything else. This is pretty much what we're talking about. Occasionally you run into a material that is so susceptible to drooling that you may just simply need a shut-off nozzle. But for the most part, you can get by with one of these two designs. And then once you've got the thing on there, make sure to pay attention to the picky details. Radius too large, radius too small, what's that going to result in? Either plastic collecting here and the sprue sticking, or leakage and the sprue sticking, or if the nozzle orifice is larger than the sprue bushing, the sprue sticking, or if the nozzle is not properly aligned, there's an undercut here and the sprue sticking. You know, these are all the things that we just simply try to fix by just shoving a piece of cardboard in there and hoping the problem will go away. If you do need an insulating layer, here again, my buddy Bazzelli has come up with something that I think works pretty well. He actually has a shim made of ballistic Kevlar. And the value of using that is you don't have to replace it every half an hour. Once it's in there, it's pretty much in there for about as long as you want to keep it there. And it does a very good job of preventing heat transfer. And if you contact him, he will be happy to sell you these little squares of ballistic Kevlar. They work very, very well, if you do, in fact, need them. But first, take care of the fundamentals. And make sure that you take full advantage of the opening in the mold. The sprue bushing has a certain O dimension. The nozzle tip should be matched as closely as possible to that sprue bushing. Now, I know this sounds like very, very basic stuff, but I cannot tell you the number of times, not only in my own plant when I worked in a plant, but also now when I go into other plants, where you see a nice big 9/32 opening on the mold, and you see a 1/8 inch nozzle tip on there. And it's like, why? Why are they doing that when it could be a 1/4 inch tip? Other things to avoid, very long nozzles. This gets into the whole thing of where the thermocouple is. Recently I worked on a project where the nozzle was so long that there was a temperature gradient from the back of the nozzle to the front of the nozzle of over 100 degrees Fahrenheit. The temperature at the back of the nozzle was actually below the crystalline melting point of the material. It actually wasn't even hot enough to melt the resin. And the temperature at the front of the nozzle was hot enough to degrade the resin. And that's all in the space of just the nozzle. So this, again, is just the fundamentals of setting the thing up correctly. If you put mixing elements in your nozzles, if you don't want to do the work of mixing properly in the screw, a lot of times people will put mixing elements in the nozzles. Those can work, but keep in mind many of those also produce a pressure drop, which makes the job of filling the mold that much more challenging. Rheostat control the nozzle temperature. I mean, I think a lot of us have seen this. You know, what's the temperature of the nozzle? Oh, it's 40%. 40% of what? What's that rheostat hooked up to? A 200-watt heater band, a 300-watt heater band, a 600-watt heater band? Shims to prevent leakage and heat transfer, we talked about that, and attempts to regulate the melt temperature in the nozzle. Once the material is all the way up to the nozzle, the temperature of the material you shouldn't be trying to change the temperature of the material at the last second. It should just be a pass-through to get into the mold from the front zone. Okay, so in summary, the hardware between the feed throat and the sprue bushing of the mold is critical to part quality and consistency. Not the speed of your controller, not the sexiness of the new capabilities of the machine, but just simply the boring details of what the hardware looks like. Proper sizing of the injection unit is crucial to being competitive. Having an abundance of first stage pressure promotes velocity control. Thermal input and shear must be balanced appropriately for the material being processed, and mixing designs and high performance materials of construction are not an expense, they are an investment. And finally, avoid unnecessary restrictions in your flow path. Do not default to higher flow materials unless you've done your homework, because higher flow materials mean less performance for that part in the field, and sooner or later that's going to come back to get you too. Because we all know most of our OEMs are pretty good at pointing the finger back to the processor nowadays. Pay attention to the little details. This is not sexy stuff. This is not glamorous. This is not 3D printing. This is just about paying attention to the picky little details, but they matter a lot. And you need to think differently about things that most of us have stopped thinking differently about. And you'll need to create relationships because you're going to need to get these new screws built. You're going to need to get these new screw tips built. And if you go to a lot of the people who do this for a living, they're not thinking differently either. So they're just going to want to send you the stuff they've been sending you for the last 40 years. So you're going to need to find people who will be willing to do things a little bit differently, cultivate these relationships, and work with them. And that's not a simple process, but it is doable. And there's a lot at stake here. And with that, I will send things back over to Trey, and what we'll do is we will start.
And while Mike is getting that set up, we've had a ton of great questions already come in, so we do encourage you to continue to send us questions. Type those in the question box located on your screen. We've had a ton already come in, and those will be sent to Mike for follow-up offline. So again, please finish your questions, and with that, I'll turn it back over to Mike.
Okay, real good. There's one here that I think is a really good question, because I want to address it, because I really don't have a good answer for you, because it's one thing I never had a chance to try, but I do want to address it because I think it's a really good question. It represents kind of the far end of the spectrum, and it came in from Garrett Reddick. A mixing screw for rigid PVC, question mark. And what he's saying is, I think the subtext of that is, are you nuts? I don't have a good answer for you, Garrett. What I can tell you is this. I was able to work with a company that designed mixing screws that worked for every material I threw at it. And the only material I never had a chance to try on it, because I wasn't running that material at the time, was rigid PVC. But I can tell you that I was able to process everything else, including acetal. I was able to process long glass fiber and keep it long, which, by the way, many mixing screws will not do. They'll just chop the heck out of the glass. So I think I'd love to be able to try it someday. I am convinced that it is possible to develop a gentle enough distributive mixing to where it would be possible with the right formulation of PVC to make it work. But I do not have any data for you, and I'm a data-driven person, so I want to make sure that I'm, clear and open and honest about this. But if you are running into challenges running PVC, and many people do, I would suggest that a different approach to the design of the screw would be an avenue for trying to open up that processing window, because I've seen it work for virtually everything else. Now, good question here from Bruce Conway. What screw is recommended for clear polycarbonate? We run a 7 melt index PC. Okay, couple of things. First of all, materials of construction, there's a lot of good information from the material suppliers about what the screw should be made of, and I would defer to them on that topic. As far as the design of the screw, I've used pulsars. That was the screw that I standardized on back in 1991. And I had very, very good success, not only with unfilled polycarbonate, but with glass-filled polycarbonates as well. Now, everyone's got their favorite screw, and one thing I've discovered in working with people on screws is that screw design invokes about as much emotion as religion and politics. Everyone's got their favorite. But here's the deal. The reason we standardize on the pulsar, because we're a custom plant, is because it worked with virtually every resin that we processed. One thing you want to avoid, unless you're a captive house running the same stuff all the time, every day through that machine, be careful of people who want to design a screw for you that is quote-unquote optimized for polycarbonate or optimized for nylon, because not that they can't do it, they can. But what they'll be doing is they'll be incorporating characteristics into that screw which will not be optimal for many other materials. And so you'll get great results when you run the polycarbonate, and when you throw the nylon in there or the acetal in there, it'll be a nightmare. So you're looking for a design that does a really good job of just gentle distributive mixing, because that works for every material. And I noticed there's a comment from a guy named Jim Fattori up here right after I started answering the question that says use pulsar screws for rigid PVC, and there's no question mark in the end of that statement, so I'm assuming that's a statement, not a question. So sounds like maybe somebody has some experience out there with that, which I'm very gratified to see. So, again, if you're using the same material every day, then you can work with a screw designer, and they will be able to tailor the material, or tailor the screw directly for the material. With polycarbonate, you're trying to keep your shear levels down, so you're probably going to be using a relatively low compression ratio. You're going to be keeping your flow paths as wide open as possible. One thing you're going to want to try and get your screw designer to do that most of them have a hard time doing is give yourself a generous radius as you blend from the top of the flight into the root. Because if it's too sharp, material will collect there, and that's where you're going to get your burned material, your held up material, your charred material. Get the builder to fill that area in as much as possible. and the word is pulsar, P-U-L-S-A-R. Now, here's the thing. This is the real world we live in. Pulsar was designed by a company called Spyrex. Spyrex was purchased a few years ago by a company called Exaloy. So Exaloy has the rights to the design. They have the people there who know how to build it, but it's not an Exaloy product. So you're going to have to ask for it. Or you can contact people who used to work for Spyrex who have gone off on their own. One guy who I can recommend to you is a guy named Mike Dorina. Works for a company called MD Plastics, actually owns the company, and he has taken his knowledge that he gained while he was at Spyrex and has turned out some nice designs, one of which he calls a posi melt. And you're just going to have to look into what works for you. You know, Westland is out there. There's a lot of people out there who have what they say is the best stuff on the market. You may have to actually run your own trials, as I have, in order to come up with what you think is the best design. I don't know, how are we doing on time? I'm showing 101, Trey.
Yeah, Mike, we've got maybe time for one or two more questions. We have, again, just a ton of great questions. So let's maybe take one or two more questions, and then we can go ahead and get this wrapped up.
Okay. Good question here from a guy named Ross Jones. Do the traditional shear rate limits provide a good guideline for limiting visual defects, even though they seem to be overly conservative for molecular degradation? Really good question. They are, you're right, first of all, they are quite conservative. I usually take the traditional shear rates that are in the mold flow programs and multiply by 2, just as a rule of thumb. That's about what I consider to be feasible. However, and I didn't amplify on this very much, even though it's part of one of my slides, sometimes what you'll run into is problems not so much with the polymer, but with something that's in the polymer, either the colorant or maybe a flame retardant, some kind of an additive that's more thermally sensitive than the polymer itself. So you have to look at the whole package and see what's your limiting factor. And that's going to be, you know, where you really have to draw your line and say, okay, this is where I have to really watch it. And this is why, as I mentioned before, in screw design in particular, gentle distributive mixing. Don't, you know, beat the material up. There's one question here which probably doesn't interest a whole lot of people because it's about thermoset, but I do want to answer it. What would you use for a 60% glass-filled phenolic thermoset? First of all, it's phenolic. If you've understood thermoset molding, you know that you do not want to put any heat into the material while it's in the barrel. So for a thermoset, you want to have an absolutely straight screw, a compression ratio of 1. No change in flight depth as you go from front to back, or from back to front, I should say. The screw is not designed to do the same thing in the thermoset process as it is in a thermoplastic process. In a thermoplastic process, you are trying to generate mechanical work. In the thermoset process, you do not. So a 1-to-1 screw for compression, and because you've got 60% glass in there, make sure you make it out of a good, hard, wear-resistant material.
Perfect, Mike. Well, again, a big thank you to Michael for just a fantastic and really informative webinar. We do encourage you to check out some of our archived webinars that Michael has put on, just a titan of information and some really great and informative webinars. So we do encourage you to check those out on our site, ulprospector.com. Just a reminder that we will be sending everyone a recorded copy of the presentation and a link to download these slides to your email address. So if you want to, again, watch this presentation or send those to others at your company, you do have the option to do that. A big thank you again to everybody for attending, and have a great rest of the day.